Sorry, Mr. Kelly.
Yes.
I can't see it.
Keep waiting. We'll see. 5.7 applications of Newton's laws. We already know that the net force, or the total force in the system, for Newton's first law, the net force is equal to 0. And the net force is going to be a combination of forces in the x direction and the y direction to make the whole system equal 0. So the forces in those individual directions are 0 to make the total force equal to 0. Or just plainly speaking, that whatever those forces are, everything adds up to 0. This is for Newton's first law. For the net force equals 0. For that condition, when the net forces are equal to 0, the object is either at rest or it's moving at a constant velocity. Because the forces in all directions will be equal to 0. X and y directions. Now we're going to explore unbalanced forces via Newton's second law within F net force, all the forces, which is equal to Fx plus Fy, all the forces in x and y directions, equal to mass times acceleration. So we're going to go from a condition of 0 net force to net force equals to ma, which is basically Newton's second law. All masses in the system are going to be moving with a characteristic acceleration.
Mr. Kelly, sorry, I still can't see the screen.
Okay, well, I'm about to be timed out, so I'm gonna stop this. Okay, so let's try this again. So those who couldn't see, 5.7 applications of Newton's laws. We already know that the net force is equal to 0. The net force in any system is the combination or the sum of all forces in the x and y directions, the horizontal and vertical directions, for Newton's first law. Newton's first law is a law of equilibrium, or law of inertia. And we've studied that law of inertia is the tendency to resist a force, the state of being inert, the state of being at rest, the state of resisting a force. And the two conditions of equilibrium are you can be at rest or you can be moving at a constant velocity. That is Newton's first law. Now we're going to explore unbalanced forces via Newton's second law within net force equals to mass times acceleration. And I already posited that Newton's third law exists within both of those, Newton's first and second law. So you can have an equal and opposite force that is going to add up to 0, or equal and opposite force that's going to produce some acceleration. The logic for the first and second laws is the same, except now we must determine which direction, Fx or Fy, has the acceleration in the system. There's many examples of applications of Newton's second law, so we're just going to do as many examples as we can today. And if there's time, we'll introduce the concept of friction. And we already know that friction, which is what I should have done Monday, because even though friction is kind of, you can intuit friction, it's kind of, I think in my humble opinion that it'd be better to introduce it before I gave the packet. So now we have a cool, even more dynamic understanding of friction. And we can, okay, when I start putting the friction arrows in there, you already know what this friction stuff means. So it's all good. I think you guys are at a point to understand that friction is always going to be going against the motion of an object. You go right, friction goes left, vice versa. Okay, so these are vectors, you know that. Let's see. Let's do one quick example of, dynamic example of Newton's second law. I want to take a look at the runway car in section 5.7. You're looking at page 113. We're going to do that, and then we're going to do, whatever comes to mind. I'm just going to just go all out with it. All right, so let's see. Move down here. So example 5.6, we have the car of mass m. Yay, variables, right? You guys love those. A car of mass m is on an icy driveway inclined at an angle theta in figure 5.11a. Find the acceleration of the car, assuming that the driveway is frictionless. is friction because it's gonna. All right, I gotta set my system up there a little bit better. Anyway, you over there. So example 5.6, and so we have this ramp situation. This is good because now we're going to change our perspective a little bit. So we treat the car as a particle and label all the forces acting on that system, the particle here, the car. So the surface is now at a slant, so our perspective is going to be slanted. If the car was going to roll down the hill, I like to have my positive x-axis going down the hill. That's just kind of convention for me. And I generally do this, have the positive x-axis be in the direction of acceleration because, well, it is going to be acceleration. So we want to have the acceleration going in the positive x-axis. You can do whatever you want, but just be consistent. This is a surface, so there's a normal force that points up like this. Now the force of gravity is always going to be pointing down towards the center of the earth, straight down. But notice something. The vector of the force of gravity here is not in the y or x plane, it's off axis. So that means that when your vector, like force, has an angle, it is made up of two parts. It is made up of a y component that is along the y-axis. See the perspective here? And an x component along the x-axis. All because this was off the axis. The force of gravity itself is off the axis. By geometry, or you can do a geometric proof on that. One year I did that. This angle is going to be equal to this angle in here. You can do that yourself if you're curious. So FG is equal to mg. That means that this is going to be mg cosine theta, and this will be mg sine because it's opposite. So that's the pretty much one major thing that changes when you have stuff at a tilt. Just imagine if this tilt goes down like so, then everything these components will merge into FG, and it's going to be Fn equals FG. But since we're at a tilt, we have to be careful and note that the force of gravity is made up of two parts. Does everybody see that? Is everybody okay with that? Can you see it? If you can, no news is good news. If you can't, let me know. All right, so those are all the forces. So the normal force of gravity made up of two parts. It's frictionless. If there was friction, it would be going back this way. And we already know that if it was moving, that the friction would be what kind of friction? If you're not talking
kinetic friction.
Yeah, it'd be kinetic if it was moving, and in this case, it's going to be moving. So yeah, if you're not talking or whatever, just mute your mic. But yeah, all good. Yeah, it'd be kinetic friction if it's moving. If it's right now, if it's static, it's not moving. It's static friction. It's always going to go up the ramp, because if we're going to assume that it's going down the ramp. So now all these forces together are going to be adding up to make mass times acceleration. This is not a force. This is what these forces add up to. So this is not really a part of the free body diagram. The forces in the free body diagram are those forces that are touching or in contact or acting through a field on the object. All of those forces added together in their components make up MA. Okay. So now that we have our perspective, we have our free body diagram, now it's time to write the equations up. We know that F net is equal to all of the forces in X and Y, no longer 0, but now here. But do both of these have MA? They do not. The only part of this equation that has acceleration in it is the X component. The Y component is not moving up and down on the ramp, it's just sliding down. So the acceleration only exists, in this case, along the X-axis. So now that we can see that, and we'll become comfortable with that the more practice we get. So all the forces in the x direction are mg sine. You're like, oh, wait a minute, cosine is along the x-axis. Well, why didn't it be cosine? Because orientation. mg sine, and there's nothing to go against it. Said the ramp was frictionless. So that's why you can see also the x mg sine theta is equal to ma. Whereas in Fy, all the forces in the y direction, vertical direction, the normal force here minus mg cosine theta. Why minus? Because it's along the negative y-axis. See that? So then we have Fn along the positive y-axis minus mg cos theta. Those forces equal 0 because there's no action, no acceleration along the y-axis. When there's friction, we're going to need this second equation because friction is going to be proportional to the normal force. And so we need to find out what the normal force is, put it back in the friction equation, and then solve. So in this case, all right, good. You got a point on your AP exam for labeling the forces, and another point for doing proper free body diagram. Way back in the day, they would like take off points for putting the components. I'm like, why are you doing that? But they just wanted, because they were sticklers about what are the principal forces that make up the total force in the system. Okay, it was Fn plus Fg. But you know, they've since, you know, taken that restriction off. So we then find the acceleration. It's very simple, right? M's cancel out, and so A equals G sine theta, and you're done. And we are done. And then you do the, yeah, I encourage you to read all through these examples, the finalize, the evaluate, categorize, you know, do all that. And when you get comfortable, you don't have to worry about that. But this is your beginning. Any questions? Okay, so that should be straightforward. Now I have a hankering to put a friction in right now, but I will wait. Well, let us go to let's go to another example I have here. And then please read all of the examples. This is like 8th grade or something. Read all the examples. Read the examples and go through section 5.7. I encourage you, just make sure you understand every example. Any questions you have on examples, you know, just fire away. But I'm on time. We're going to go to a problem in the text. Let's take a look at, I have number 26 here, but that's from the other book. But I think it's the same one here. If you're looking at the problems, go to page 130. And yeah, let's go to number 28. This 26 here is similar, but yeah, we'll just bounce around. I mean, today is just examples. All right. Yeah, page 130. Now, we have this ramp situation. We have a pulley. And it comes over here. Okay, circular. Draw free body diagrams of both objects. Assume the incline is frictionless. Mass 1, which is this guy, is 2 kilograms, and this is going to be 6. The angle theta here, always with the x-axis 55 degrees, that's 35. Find the accelerations of the objects and the tension in the string and the speed of each object 2 seconds after they're released from rest. So we got a lot going on there. We got kinematics, we got forces. You can even do this in terms of energy when we get there. Once you know the speed, I mean, it becomes like this huge physical, like universal problem once you get all your physics behind you. But only in the Newtonian world. We can't do quantum mechanics here. Masses are too big and wavelengths are too large. And so we'll deal with that when we get there. Let's get the free body diagrams on each one. I'm going to tackle this guy first because he is the toughest, if you will. It's very similar to the car on the ramp. Now, one thing that to keep in mind with a system like this, that the tension in the strings is going to be uniform. The tension is just a one rope. So it's not like T1, T2. There's a problem where there are different strings. Right now, the pulley is massless. But when we get to torque and moment of inertia, that pulley is going to be a factor. It's not going to be massless. We're going to have to consider it. We have to consider the shape of the pulley, whether it's circular, whether it's spherical, whether it's hollow, whether it's rectangular, whatever. Depending on the shape, the geometry, the moment of inertia is important, and that's going to be a factor into what kind of torque that pulley is going to apply, and angular acceleration that we need to figure out, and blah, 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 blah. So that's down the road. All right, so Mighty's mic is on. I can hear sirens. Okay, so let's get the 6 kilogram free body diagram. So surface is at an angle, so right, so the normal force is perpendicular from that surface. And then we have FG off axis, because it's always going to be pointing straight down. Gravity, I don't care what you do, you tilt your ramp. I'm sorry, but you have to mute your mic. Who is that? All right. So, Selena, is that you? Whose mic is that? Please mute it. So that's going to be. All right. mg cosine theta. mg sine theta, just like before. So you get into the rhythm of that thing. And then, now, here's the deal. Okay, if this was 6 over here, the system would accelerate towards the 6 because it's more massive. It's going to go down. But in this case, the system accelerates down the ramp. So if this was 6 and this was 2, then my acceleration would be going this way, and my tension would be going in the same direction as it. And we'll get into that. The tension is still going to go that way, but the acceleration, which would go up the ramp if this was 6, it's not going to go up the ramp, it's going to go down. Okay, let's see that. So bigger mass is going to pull the guy down. So the acceleration is this way. So all along the positive x-axis. I like to put my positive x-axis with acceleration. There's been examples in the book, and probably even in this one, where we have this negative acceleration thing, and they have tensions doing all kind of crazy stuff. Long time ago, developed an easier method than what they want you to see in the text. So,
Mr. Kelly.
Yes.
So we look at the masses and we determine where the tension is directed.
Yeah, we're going to be doing that right now. So, so acceleration is going down the ramp, and tension is always going to be going towards, like, remember that packet is always going to be going away from the object, or to the source of its tension, which is the pulley. So the tension is going to be going that way up the ramp. And here's the thing here. It's our first time we've seen this. All forces that do not move with the acceleration A vector here, with the acceleration of the system, are going to be negative forces. They're counteracting, they're going opposite. So this tension, even though it's the same in magnitude, its direction is opposite this mass here because it goes against the acceleration towards the pulley. So it's going to be negative T. Everybody understand that? No friction. If there was friction, there would also be an arrow going up, and it's going to be negative FK. So you can understand, you can appreciate friction, because friction is always going to be negative. It's always trying to go against you. It's taking energy out of your system. It's going to start slowing you down. It's going to perturb everything. It's necessary, but it's going to be the source of taking stuff away. So it's also why it's negative. This will be positive, this will be negative because it's negative y-axis, negative, and we're good for that particle, that box. And so now the free body diagram for the hanging 2 kilograms is easier because now the tension is going to be positive because that's going with the system. So the entire system is moving together. But when they say acceleration of the objects, that's implying that they have different accelerations. They don't. They're moving together. This is the system of equations in real life. The system accelerates uniformly as one. They have a common acceleration. They're both going to be sliding together. This guy slides down. You can't see my finger. But yeah, they slide. As he goes down, this guy goes up. Same rate, same acceleration. Now, the real rub would be you can have a situation where this thing could be elastic or a spring, or it's not uniform tension. Now we got all kinds of problems, but we're not going to deal with that. I'll have to here. T goes up, and then the force of gravity here, I'm just going to call him mg. That's going to be negative because it's going against the acceleration of the system. Acceleration goes up and down. Up and down. Okay, so we're good with the free body diagrams for this guy and for this guy. So now what we need to do is get our equations for both. So I'm going to say Fx for the 6 kilogram mass. I'm going to say Fx for 6 kilogram mass is, so he has two. He has two equations of force because he has an X and a Y direction. This guy just has Y direction. So that's why I want to be explicit. But they all add up together to make MA. Because the whole thing's moving as one unit. Okay, Fx6, this is M G sine theta. Okay, minus T, because he's in the x-axis, even though negative, but the x-axis. Minus T equals anything else? No. That's going to be equal to MA. Because along his x-axis, he's moving with an acceleration. The acceleration is along the x-axis. And Fy of 6 will be normal force.
Mr. Kelly, are those the sum of the masses or?
No, this is just, good question. No, this is just M6. I mean, I could, you know what, I'm going to, because normally I do M1, M2, but we know that this is 6 kilogram mass only. 6, 0. And then we're done with the 6 kilogram mass. Now we go to the 2 kilogram mass. He just has one in the Y direction. Tension and minus mg equals m2a. Because it's an acceleration on that object along his y-axis. But along the 6 kilograms y-axis, there's no acceleration. This is very important to set it up this way or some kind of way for it that you can see it, because it's a system of equations, just adding everything together. Hence, the t's can cancel out. See that? So now you don't have two unknowns. And you don't have to deal with this y equation because it's irrelevant for now. Fn is equal to mg cosine theta. Good. What can you do with it? Nothing. And since to find acceleration, both. So just add these two guys together. Mg sine theta minus mg, right, equals m1 plus m2a, m6 plus m2a, right? Because they're moving as one system. That's why you add them. They're on the side of the equal sign, m6 plus m2. Now you can get the equation for a, which will be mg sine theta minus mg over m1 plus m2, m6 plus m2. You can put your numbers in there and you got your acceleration. Sound good? Okay, so let's make sure mg sine theta, this guy goes away, minus sign goes away, minus. Okay, so that m is the m6. This is 6. Sine of 55 minus, this is 2, the 2 kilogram guy, times 9.8 divided by 8. Why don't you do that real quick and check your answers for you, what we should be getting. Look at the other ones. We should be getting 3.57. See if you guys get that.
Mr. Kelly, could you explain again what did we adopt to get the Fnet acceleration?
I will, but let's get this here first. Make sure we get the right answer. Let's get 3.57. This first one should be 48.16 minus 19.6 divided by 8. Looks good. Okay, 3.57. Here's second squared. And then the rest is pretty easy because usually these problems, the first one is the longest or hardest, and then the other ones is domino. You can get the tension in the string, uniform tension. We can back substitute as we did in any system of equations. We can just take this one, a little less messier than this one. So T equals to M2G plus M2A. Right, because this would be that. So we just have M2 G plus A. Go ahead and do that. 26.7 newtons of tension. Then, what do you think we're going to do for part C? Let's find the
Kinematics
speed.
equation.
Kinematics, exactly. So we'll find the speed of each object 2 seconds after they are released from rest. So we know that vi is equal to 0. Takes 2 seconds for them to fall. So we have no distance, so we can't use that particular kinematics equation, but what's the best one we can use? Selena, got any ideas for us? What's the best equation we can use here? We know we're trying to find the final speed. We know the initial speed is 0 because it starts from rest. Takes 2 seconds. Of those 4 equations, what's the best?
Can I see the equations, Mr. Kelly?
Well, you have them in your textbook and your notes. But I can, you know. You're correct, Nicole. All right. Oh, crap. Okay, so that's E. So we use this guy. It's the most useful. Okay, goes away. 3.57. That's 2. And that's roughly 7-ish seconds. Seven. 0.14 meters per second. That. Okay, sounds good. Part D. Right? Start getting creative, right? Find the distance, 2 kilogram mass, gobbled up. Go for it. You have its acceleration uniform, you have the time, initial speed is 0. Anybody get it? Just chime in. Of course, if I put friction in there, it's going to change a little bit. Acceleration will change. Acceleration will actually be smaller. Yeah, it's not going to move as quickly, take more time. Right? Let's see. Emmanuel, are you here? Yes. Did you get the answer?
No, I'm trying to find the paper I wrote the equations on
Oh.
because I cannot find it, but I think I know what to do.
Okay, well, you can look back at chapter 2 for those equations.
Yep.
All else fails. Okay. Well, you know, I will write them up here. You know, I'm not gonna do this every time. Well, delta x, delta y, and projectile motion. Okay, we have a comment or question. Yes, we can do that one, or we can do the time one. Sure. Okay. Let's see, then we got that. Okay. Yeah, I was thinking about using this guy. Because I mean, I can get rid of no. all right. Then, E delta Y or delta X. Let me use the second guy because I can just faster. BI is 0, so that's just 1/2 A squared, 1/2 3.57 times 2 squared, and 4 times 3.57. What? That's interesting. 0.57. So it traveled 7.14 meters up.
Same as the acceleration, right?
Same as the velocity, which is interesting. So 7.14 meters. All right, whatever. Check that with this guy. Nicole, did you get the same thing using this last equation? You should.
I got that.
Yeah. This is very interesting. But it is, I mean, it's no real, like, yeah, no worries. Yeah, okay, that's just next thing. Here's a problem for you. Let's get you guys to do something. Why don't you try number 26 in the text? And let's talk together, and let's do that. So set up a breakout and get you. I'm gonna assign manually, and okay, and un segundo. Sin, you had a question before on the forces up top, or did you get your question answered?
Yeah, when we find the acceleration there, we added the fx for the one object to the fx to the second, right? For fnet.
Yeah. You talking about the previous problem was 6 and 2 kilogram masses?
Yes.
Yeah, it was the fx force for 6. Fy did not have an x component because it's just hanging vertically. I mean, I don't think I answered your question.
Could you show the acceleration part when we found the acceleration?
Okay, from this point forward. Okay, that's what you mean. Okay, so for the 6 kilogram mass here, it has forces along the x-axis, one pointing down, one pointing up, mg sine theta in the positive x, and then tension in the negative x. Just let me know if, okay, do you understand this part?
Yeah, it's like down the line.
Okay, right here.
Below, yeah, below the line. So we adapt for acceleration. We adapt fx 6 kilogram and fx kilogram.
Yeah, this would be the 6 guy because I'm taking him from the first equation for the 6 kilogram mass, and then this is the 2. And then, where M1 is 6 and 2 is 2. 6 times 9.8 sine 55 minus 19.6 over 8. And then comes out to 3.57.
All right, I think I get it now.
All right. Okay, and then we come all the way down to 26. Same logic. It's a little bit easier. Because we don't have a ramp. So we have a normal force for the 5 kilogram guy. And minus Fg. And then he has a tension that goes this way. And it's positive because it's going in the direction of the acceleration. So again, our perspective, x, y. And I like to have my system acceleration be positive a on the positive x-axis, indicating the direction of the acceleration in the system. So this is t. All forces moving in that direction, moving with the acceleration are going to be positive forces. And then for this guy, he's going to have minus t because it's going against, and this is going to be m plus, I'll just call him m2g for the second mass. So m1 is 5 kilograms, m2 is 9. Oh, going to the center of the earth, it's gravity. No, I mean, that's true, but this the vector is positive with acceleration. That's what you do. Fx1, just t equals m1a. Nothing else happening. If there's friction, it'd be t minus fk. Then y1, accelerating vertically, and y2, negative t plus d, 2a. All a system of equations. You can even use a matrix for this. Do anything crazy, but it comes out to be a matrix. Gauss-Jordan elimination, do the same thing as you would system of equations. So this is unimportant. These tensions cancel, very convenient. And we're just left with m2g equals a. Seems good, huh? m1 plus m2. 9 kilograms times 9.8 divided by 14. And that's roughly 90. 6.3 meters per second squared. Let's get that. So that's what you should have. Any questions?
Can I see the equation you got for A again?
Yep. Right here. Just added, I mean, I'm just going to go back a little bit. So this, remember, all this stuff is on the other side of the equal sign. And this is what you do here, operation T, those go away. This is irrelevant, only when there's friction. Any private questions or questions on the method? So Joy, you got that?
Yeah.
Okay, and then again, the method. Got your picture, draw pictures all the time. I was any problem, draw a picture out. Get your perspective, x, y. X is going to be direction of positive acceleration. Do your free body diagrams, equations, and solve for what you need to solve. Acceleration, usually, then you want to solve for tension. You maybe want to find out how much time it takes, what the distance traveled. So now we're going to start to integrate forces and kinematics. Next, we'll be doing energy, forces, kinematics, momentum, energy, forces, kinematics. You build this huge array of a physics phenomena for you to use. So any problem, you can use all Newtonian mechanics. And then as you get adept in the quantum mechanics field, kinematic operators, force operators, you know, you can start doing all that stuff. It's kind of weird down there because probabilities, wave functions, some things, well, this is more probable, the electron's going to be here, more than likely, least chance for being over there, all because of its wavelengths being very small and the wavelength of these guys, although these masses are made up of waves, but the wavelengths are too large to be using quantum mechanics on. So, but anyway, so there's that. So let's go to number 23. Your textbook. Okay, next page here. Who wants to tell me what would the spring scale read for part A? We got the spring scale attached to these two masses. What do you think it's going to read? Just kind of crudely draw this. So tension goes back up. Anybody want to do that? What is the tension value? What do you think the spring is going to read? First of all, what would this equal? What would the tension equal?
Negative MJ.
Well, numerically.
Would it be like negative 5 times 9.8?
Well, here, yeah, the tensions are going to be equal to mg equals 5 times 9.8, correct? And that's roughly 750-ish, right? Times 5, 49. What does the scale read? This is also 49. It's 5 and 5. Does it read 100? 50? 0? Anyone? No guesses?
Would it be 100 because there's two tensions on, or like one tension on either side?
I can see why you would say that. But remember, these tensions are going opposite each other, counteracting.
Ah, so would it cancel out then?
Not cancel.
Or
They would be.
Would they balanced? They'd be balanced?
They would be, but then what's the value going to be?
0?
Nope. That because that goes
50.
back to Emmanuel's point of being canceling out.
then 49?
They would be 49 because they're equal and opposite. One guy pulls one way at 49 and pulls the opposite way at 49. So the spring scale is just reading 49. Newton's third law. See that? I can see why you say cancel, but we have a pulling. It's like we would have a push. One guy, you know, like if we have an object being pushed on, let's say this is object 2 or something, F1 on 2, and this would be opposite 2 on 1. Same, we switch the visual. This is pulling 1 on 2, equal and opposite 2 on 1. This is what's going on here. You guys see that? Is that okay? Comfortable? This will be push, and in this case, we have a pulling. Tug of war, tug of war. Two masses pulling. String is going to be tight at the same strength. right? But it's this, it's the team that has, you know, maybe more friction or more mass. At some point, they pull with an unbalanced force that causes the other team to go forward. But in the moment that they're pulling and nothing's happening, the force is the same. Think static friction. I can't push my object yet, or I can't pull it yet because those forces are balanced. This is balanced, you guys are correct, but the force is the same. The readout is same force, equal and opposite. Okay, part B. Who has that one? That one should be a little easier. What does the scale read? Remember, tension is going towards the scale. That's the source of its tension. So it's and then same here. MG. That would just read 49. You guys see that? It's comfortable. That's pretty easy. That's equal and opposite. Equal. Yeah, equal opposite. P equals mg 9.8. So that one's also 49. And then letter C. What about that one?
Is it 98?
That would be 98. Perfect sim. Because the tension is going to be reading what both are pulling at the same time. Those blocks are not pulling on either end of the scale. They're both pulling on the same scale, but in one direction, down. So the tension is going to read both. Tension's up here, and then we have both of the weights. You can just say 2 times 5, 49 times 2, 98. Anybody not comfortable with that? Is that okay? Because both of those masses are working together. And then part D. What would the tension be there? What would we have to do? Again, for right now, the normal force is not important. Tension is equal and opposite this guy. So 50 sine of 30. That's roughly 24.5 newtons. So, I mean, nice little scenarios with the pulleys. There's another neat one I might just include for your homework. There, which is number 32, if you're thinking a little bit more. So next class, we will talk about friction. We will include friction in there. And then, you know, we can literally do the same problems with having just friction going the opposite way. And then our normal force will become important. Any other questions? Okay, we have 5 minutes. Let's see what we can do here. I want you to take a look at example 5.7 on page 114. Okay, so there we have 2 blocks of masses M1 and M2. Just kind of, see what time we have. With M1 greater than M2 are placed in contact with each other on a frictionless horizontal surface as an active figure 512A. A constant horizontal force F is applied to M1 as shown. Find the magnitude of the acceleration of the system. So with these type of questions, which is a neat one, we can see that in the problems, like number 54, just be careful. Just take it step by step. You use your logic. What's your perspective? Well, it's regular XY plane, right? The camera should bring it up. Important one. There. Okay, so X, Y, okay, you got that still going, and then just like they did here, put your free body diagrams, draw your free body diagrams for each object. F is pushing to the right on mass 1. There's a force in between them that's going to the left, normal and weight, right? And then with the contact force of mass 2, F is not going to be in contact with mass 2 because it's not in direct contact. The contact force is that P1, P12 force, the force of 1 on 2, and then normal and weight. And then you just put your stuff in the X and Y axes and do like we normally do, and that's what they did here. F is equal to M1, M2, because the contact forces are equal and opposite. They cancel out. Put them in there and see for yourself that they cancel, and then you get that expression for the acceleration in the X direction. Is everybody looking at that? Example 5.7, you understand that? Any questions? And then part B, determine the magnitude of the contact force between the 2 blocks. So we know in the example there, number 2, the forces in the X direction equal to P12, equal and opposite P12 on P21 is the same thing, just say P. And that contact force is just going to be equal to mass 2 times acceleration. And why mass 2 and why not mass 1? Because the perspective. They're choosing 1 on 2 as opposed to 2 on 1. Then it would be just M1. But does everybody understand that equation? Fx P12 equals M2AX. Why they did that? How do they get that expression? Well, they substituted the expression for A that they got in part A and multiplied it by F, that's part of part A. So basically they took M2, which is there, and number 2. So you can see that M2AX part, and then they just said M2, and they just did the expression for AX from part A. And that's why it comes out to be that. F M1 plus M2, or how, simplify M2 over M1 and times F. Okay, so that we'll do it. So Julius, you have time